Let's talk about transformers. They are the silent, unassuming workhorses of our entire power system. I mean, you see them everywhere, but you probably don't think about them much. They just work, day in and day out, making our modern lives possible. But these incredibly important assets face constant, invisible threats. And in this explainer, we're going to pull back the curtain on the ingenious systems designed to protect them from, well, catastrophic failure. So let's get into it.
And yeah, the stakes could not be higher. This quote from Wiring Guru just says it all, doesn't it? Failure isn't some slow decline. It's instant. It's violent. We're talking about a multi-million-dollar piece of equipment turning into scrap metal in the blink of an eye. And that's exactly why this hidden network of guardians is standing watch, ready to react in milliseconds.
All right, so what are we even protecting them from? Well, as it turns out, the threats a transformer faces are coming at it from all angles all the time. Some dangers start from deep inside the transformer itself, while others come from the wider power grid it's connected to. These dangers really fall into three main buckets. First up, you've got internal faults. These are problems brewing deep inside the guts of the transformer, in its windings or its core. Then you have external faults, like a short circuit happening way down the line that sends a massive destructive surge of electricity racing back toward it. And finally, there are just abnormal conditions. You can think of this like the transformer getting a fever, maybe from too much voltage or just plain overheating. If you don't catch any of these, you're looking at fires, explosions, and, you guessed it, widespread power outages.
So how do you fight all these different kinds of problems? Well, you can't just use one solution. Engineers have built a really comprehensive, multi-layered defense system. The best way to think about it is like a three-layered shield, with each layer designed to spot and stop a different kind of threat before it spells disaster.
At its heart, this is what transformer protection is all about. It's not just one gadget, it's an entire system of devices working together. And they have one critical job: sense a fault the very instant it happens, and boom, disconnect that transformer from the grid. It's an automated, super high-speed guardian angel.
The first layer of that shield is electrical protection. Pretty straightforward, right? These are the sentinels that are watching the flow of electricity itself. They're constantly looking for any telltale signs of trouble, like a dangerous spike or a massive surge in the current. Now, the second layer is mechanical protection, and this is where things get really cool. These devices aren't looking at the electricity, they're looking for the physical symptoms of a problem inside the transformer, things like a sudden buildup of gas pressure or a violent rush of oil inside the tank. And the third and final layer is thermal protection. This one works pretty much like a thermometer. It's constantly monitoring the temperature of the transformer's oil and its windings. If things start getting dangerously hot, this layer kicks into action. Sometimes it just turns on some cooling fans, but if things get really bad, it'll take the transformer offline completely to stop it from having a meltdown.
Okay, let's dive into that first layer of defense, the electrical protection. We're going to look at a classic example, a device called an overcurrent relay. Its whole job is to stand guard against those dangerous electrical surges.
The idea here is actually super simple, but it's brilliant. The system sets a safe maximum level for the electrical current. If the current flowing through that transformer ever goes above that preset limit, that digital tripwire, it instantly fires off a signal to a circuit breaker and disconnects the transformer from the power grid. Simple as that. So how do you know where to set that tripwire? Well, first things first, you got to know what's normal. For a pretty typical 100 kVA transformer, that's just a measure of its power capacity. The normal, everyday operating current is right around 5.25 amps. This is its baseline, just doing its job.
Now, you can't just set the tripwire right at 5.25 amps, right? Because power demand goes up and down, and you get tiny, harmless surges all the time. To stop the system from shutting everything down for no reason, engineers call that nuisance tripping, you have to build in a little bit of a safety margin. A buffer of about 35% above normal is a pretty common choice. And that gets us to our magic number. You add that 35% safety margin to the normal operating current, and you land on your trip threshold, 7.1 amps. This is called the pickup current. For this transformer, any current below that is business as usual. Anything above it, that means there's a fault, and the protection system is going to kick in instantly.
Okay, so that handles the big electrical surges. But what about the sneakier problems? The ones that start small, deep inside the transformer, and don't immediately cause a huge spike in current. For that, we turn to our second layer of defense, and a really, really clever piece of mechanical engineering.
Say hello to the Buchholz relay. It's basically a gas and oil flow detector that sits in the pipe between the main transformer tank and its oil reservoir up top, which is called the conservator.
You can think of it as a little watchdog, listening for whispers of trouble from inside. And what's so cool about it is that this one simple device actually gives you a two-stage warning.
Okay, so stage 1 is the alarm. This is for those minor, slow-developing faults. Imagine a tiny piece of insulation starts to break down. This slowly creates little gas bubbles, which float up and get trapped inside the Buchholz relay. As more gas collects, it pushes the oil level down inside the relay, and an upper float drops with it. That drop closes a switch, and an alarm goes off. It tells the operators, hey, something's starting to go wrong in here long before it becomes a disaster.
But what happens when things go from bad to really bad? And fast? That's stage 2, the trip. If a major short circuit happens inside, gas is created so violently that it causes a powerful surge of oil to rush out of the main tank. This wave of oil slams into a lower flap inside the relay, pushing it forward. That movement closes a totally separate switch, and this one is wired to immediately trip the main circuit breaker. No alarm, no warning, just disconnect, now. It's all about preventing a catastrophic explosion.
All right, so we've got our electrical guards for external threats and our mechanical guards for internal ones. But here's the thing, they don't just work alone, in a bubble. The real genius here is how all these different systems work together in a perfectly coordinated defense, not just to protect the transformer, but to keep the entire grid stable. This is where a really crucial concept called time grading comes into play. Just look at this table for a second. If a fault happens on a power line downstream, the circuit breaker for that line is set to trip the fastest, in about half a second. The transformer's own relay actually waits a little longer, around 0.8 seconds. Why the delay? Well, it's pretty smart. It's giving the downstream breaker a chance to clear the fault first. It only acts as a backup, but if the fault is inside the transformer itself, its own protection trips instantly. No waiting.
And that, right there, is the whole point. This intelligent, tiered response is called selective clearing. The goal is to make sure that only the smallest possible piece of the grid gets disconnected to isolate a fault. It's what stops a problem on a single street from causing a citywide blackout. It's what keeps the lights on for everyone else.
So from overcurrent relays that act like digital tripwires to gas detectors that can feel a surge of oil, these silent guardians are on watch 24/7. They make decisions in fractions of a second to protect our power supply. They are truly the unseen, unsung heroes of our modern world. Which, it leaves you with one final thought. These invisible guardians react in milliseconds. What does our world look like the moment they don't?